Now we'd like to look at transforming capacitors to the phasor domain. Here we have a capacitor driven by a sinusoidal voltage source, and we'd like to find the current through it. Then recall that the impedance is the phasor voltage divided by the phasor current, so we need to find the phasor voltage and the phasor current. To begin, well, we know the voltage across the capacitor, Vc of t, is simply given by our amplitude, Vm, e to the j omega t. Recall that the current through a capacitor is C times the derivative of the voltage across the capacitor with respect to time. Well, if we look at the equation above, we can see that the derivative is going to be j omega times C times Vm e to the j omega t. We can now take the phasor transform of the voltage, which will just be the magnitude of the voltage at angle 0. To transform the current to the phasor domain, we take the magnitude. J is not a magnitude, recall, so we'll have omega c times Vm at angle. Now the j out front is an imaginary component, and that has an angle then of plus 90 degrees. Knowing the phasor voltage and the phasor current, we can now express our capacitive impedance, Zc, as the phasor voltage, Vm at angle 0, divided by the phasor current, or omega c times Vm at angle 90 degrees. The voltage magnitudes will cancel out. It would be somewhat surprising if the impedance depended on the voltage itself. And so I'll have 1 over omega c at angle minus 90 degrees. Recall that dividing by an angle means that we subtract the angles. And this is our impedance in polar form. People also like to use rectangular form, where the impedance will be 1 over j omega c. And based on this, you can see now that in the time domain, where we'll have a capacitor C, it will get transformed into the phasor domain. We use the same symbol in the phasor domain as in the time domain, but now it has a value of 1 over j omega c. And I want you to note two things. One, the first thing to note is that the impedance is the factor that the current is multiplied by to get the voltage. So we can see that the voltage will lag the current by 90 degrees. The negative sign in the polar form indicates lagging, or you can see 1 over j will give us a minus 90 degrees as well. The second point to note is that if omega is equal to 0, which is really just a DC frequency, then the impedance of the capacitance, Zc, will be infinite or an open circuit. And this lines up with our regular understanding of capacitors. Well, that's what capacitors look like in the phasor domain. Let's proceed to look at inductors in the phasor domain and see how they behave. To transform the inductor to the phasor domain, we have to find the impedance of the inductor. So once again, we're going to drive our circuit element, the inductor, with a voltage source and find the current that flows through it. We'll express both of those in phasor form, take their ratio, and that will be the impedance of the inductor that we're looking for. So the voltage across our inductor, VL of t, is simply equal to the magnitude, Vm, e to the j omega t. Recall that the current through an inductor as a function of time is 1 over L times the integral from minus infinity to the desired time of the voltage as a function of time. This is where sinusoidal sources are particularly helpful. You can see that I have 1 over L as a constant, so I can put that there. If I take the integral of Vm j to the omega t, I'll have Vm over j omega e to the j omega t. I can now take the phasor transform of the voltage, which will simply be the magnitude at angle 0. I can take the phasor transform of our current. I'm going to have our voltage magnitude, Vm, divided by j omega L, putting all the constants together. And the angle because the J is on the bottom, gives us minus 90 degrees, and recall that the J's don't show up in the magnitude because it's an indicator of real and imaginary components. Now I can go on and find the impedance of the inductor, and so I can express that as the phasor voltage, Vm, at angle 0 degrees, divided by Vm over omega L at angle minus 90 degrees. You can see that the voltages once again cancel, and I'll be left with omega L at angle plus 90 degrees, and that's our impedance in polar form. Alternatively, I can express the impedance in rectangular form. Plus 90 degrees means we'll have J omega L, and that's our impedance in rectangular form. Now you can see that if I have an inductor in the time domain of value L, when I transform it to the phasor domain, I'll have an inductor. Again, we use the same symbol, only now it will be J omega L as the value of the inductor. And note here two things. The first one, the phasor representation of the inductor, the impedance, is the ratio that we multiply the current by to determine the voltage. And you can see that the phase now will be 90 degrees positive, so the voltage will lead the current by 90 degrees. The second point to note is that when omega goes to 0, then the impedance of our inductor will be equal to 0, which is simply a short circuit. And remember, when omega is 0, that's as if the frequency was 0 or DC, and so our inductor appears as a short circuit for DC. To summarize our findings, let's put them all together in a table. We started out with the resistor, where V of t was simply given by R times I as a function of time. But in the phasor domain, we found that the phasor voltage, which we'll represent as uppercase, will be given by the impedance of the resistor times the phasor current, where ZR was simply equal to R. So here's our time domain, and here's our phasor domain. The inductor, recall that V of t was given by L times the derivative of our current with respect to time. And when we transform that into the phasor domain now, V will be nothing other than the impedance of the inductor times the current, where the impedance of the inductor, ZL, is equal to J omega L. And for our last component, the capacitor, our voltage V of t now is equal to 1 over C times the integral of our current I of t dt from minus infinity to the desired time. When we transform this one to the phasor domain, we find that the voltage will be equal to now the capacitive impedance, ZC, times the current, and ZC, as we've just found, is equal to 1 over J omega C. Looking now in the phasor domain, you can see that resistors look just like resistors in the time domain, but in the phasor domain, inductors and capacitors are functions of frequency, or omega. That's why we refer to the phasor domain as the frequency domain sometimes. And you'll note that as the frequency goes up, the impedance of the inductor increases, and the impedance of the capacitor goes down with increasing frequency. We'll now proceed to take a look at an example of how to analyze a circuit in the phasor domain.